Okay, we continue with two more special limits from section 1.3. They're both trigonometric limits. The first one is the following. The limit as x goes to 0 of sine x divided by x is equal to 1. Now, we can have anything upstairs and downstairs in this fraction as long as they're the same and as long as they're both going to 0. For instance, I could write this more generally as the limit of any quantity, which I'll denote by box, going to 0 of sine box divided by box, and this equals 1. So for instance, if I had the limit as x goes to 0 of sine 2x over 2x, well, the 2x in the numerator inside the sign and the 2x in the denominator are exactly the same. And if x is going to 0, certainly 2x is going to 0, so this is equal to 1. Let's go ahead and see if we can solve a limit which is not so obvious, again using this pattern. Let's say we have something along the following. The limit as x goes to 0 of sine 2x, this time divided by 3x. Now, what we have up in the numerator and then in the denominator, the 2x inside the sign and the 3x outside the sign, they're not the same quantity, even though they both happen to be going to 0. So, for me, if I'm solving this limit, if I'm trying to figure out how to evaluate this limit, I would really like this quantity right here and this quantity right here to be the same. So I'm going to go ahead and make them the same. I'll write this equals the limit as x goes to 0 of sine 2x divided by 2x. Now I can't really do that, of course. I've made these the same, but I can't magically turn a 3 into a 2. So to fix that, I'm going to multiply on the bottom by 3/2. 3/2 times 2 is 3. And so if you look at this, now I haven't really changed anything. This equal sign is no longer a lie. This is really the same as this. 3/2 times 2 is 3, and so this all looks the same. When I pull this fraction out of the denominator, the limit as x goes to 0 of sine 2x divided by 2x, if I put the 3/2 out in front, since it was on the bottom before, now we can write it as 2/3. 2/3 times sine 2x divided by 2x. And since this is a constant, one of the first things we learned about limits is that we can pull the constant out in front. So this is equal to the limit. This is equal to 2/3 times the limit as x goes to 0 of sine 2x divided by 2x. This is the same now, and 2x is certainly going to 0 because x is going to 0, and so this is equal to 2/3 times 1, which is equal to 2/3. We have one more special limit that I would like to introduce, very much like this first limit, sine x over x as x goes to 0 is equal to 1, and that is this. The limit as x goes to 0 of 1 minus cosine of x all over x is equal to 0. And again, as long as what's up here inside the cosine and what's down here are the same, and it's going to 0, then this limit equals 0. And you can use it very much like you use the limits up here. Well, that's pretty much it for section 1.3. I want to move on to section 1.4, which is about continuity and one-sided limits. So section 1.4, continuity and one-sided limits. We're not going to get very far in this section, in this one lecture. We'll continue this in our next class. but I do want to talk about the idea of what it means for a function to be continuous at a point. I guess it would help if you could see what I was writing. Okay, so I do want to talk about what it would mean for a function to be continuous at a point. And that's relatively easily defined. So here's a definition. We say a function f is continuous at x equals a if three things are true. 1, f of a must be defined. The function isn't even defined there. It certainly is going to have a break there. It can't possibly be, for just a second, it can't possibly be continuous. Secondly, the limit as x goes to a of f of x must exist. So as x gets closer and closer to a, the values, the y values, f of x is the y values, must be getting closer and closer to some number. And last, these two values must be equal. So the limit as x goes to a of f of x equals f of a. If any one of these three fails to be true, the function is not continuous at x equals a. Let's take a look at an example visually. Say we have a curve given by y equals f of x. Here is, say, x equals a. We can see visually that this function, if this is y equals f of x, is certainly not continuous at x equals a. We have a hole in the curve there. Let's see what goes wrong. F of a at this x value, which I've just called a here, if we take a look at our picture, we can see that f of a, we look for the closed circle, and that's at height 1, 2, 3, 4. So f of a equals 4. That certainly exists. If we take a look at the limit of f of x as x goes to a, well, that certainly exists too. As we walk closer and closer to a, but not equal to a, we check these y values, they seem to be getting close to 2. So looking back at the definition, we see that this function at x equals a passes the first two parts. F of a is defined, f of a was 4, and the limit is as x goes to a of f of x exists, that equals 2. Unfortunately, those two values are not equal. So the limit as x goes to a of f of x does not equal f of a. This one's equal to 2, and this one's equal to 4, and 2 and 4 are certainly not the same. So this is one way a function can fail to be continuous, and we're going to see other ways during our next lecture.